In the last lecture, we were attempting to calculate the effective conductivity of a composite material consisting of particles embedded in a matrix, spherical particles of radius r, whose thermal conductivity Kp is different from the thermal conductivity of the matrix Km. And since the thermal conductivity is different, the flux lines or the thermal flux lines around the particles either bend towards a more conducting particle or away from a less conducting particle, and because of this there is a disturbance to the heat flux, and this results in a modification of the conductivity of the composite in comparison to the conductivity of the matrix. And this we were attempting to evaluate in the dilute limit, where the disturbance to the temperature field around one particle does not affect the temperature field around another particle. So, that is the limit in which we are attempting to find out what is the disturbance to the heat flux due to the presence of the particles. So, therefore, each particle can be considered to be placed in a temperature field which is a linear function of the z coordinate far from the particle, where the z coordinate is the direction of variation of the temperature. So, each particle, the temperature field around each particle will be of the form the temperature at the center plus a linear plus a temperature gradient times the z coordinate far from the particle. Of course, the temperature close to the particle will be different, but the temperature far from the particle will be of this form, constant temperature plus T prime times z in the limit as r goes to infinity. Okay. So, that is one of the boundary conditions where z is equal to cos theta. At the surface, we have the particle and matrix temperatures are equal, and the particle and matrix normal fluxes are also equal, okay, at the surface. Okay. And the equation is the Laplacian of the particle temperature is equal to 0, the Laplacian of the matrix temperature is equal to 0. Okay. And I had written down the expression for the temperature field and the Laplacian of the temperature field. In this particular case, there is no variation in the phi direction around the z axis, and therefore, there was variation only in the radial direction r and the theta direction. The surface is a surface of constant r, so there is a dependence on r, and far from the particle the temperature depends upon r cos theta, which is z. Therefore, there is a dependence on theta as well. So, this is the Laplace equation for the temperature, okay. And we were attempting to solve this by separation of variables, where the temperature was written as some function of r times some function of theta, that is f of r times g of theta. Substitute that into the Laplace equation, multiply by r square, divide by f times g to get this equation, in which the first term on the left depends only upon r, the second term on the left depends only upon theta, and therefore, both of these have to be constants. And we were attempting to find out what is the value of this constant. Now, theta varies from 0 to pi, okay. Therefore, the boundaries for theta are 0 and pi. However, at the boundaries of the theta coordinate, there is no physical boundary. Theta is equal to 0 is the plus z axis, theta is equal to pi is the minus z axis. At these locations, there is no physical boundary. Okay, so, I had said that the boundary conditions in the theta direction have to emerge from symmetry, and we were trying to examine how these boundary conditions emerge from symmetry. So, I defined another coordinate psi, which is cos theta here, okay, and expressed the second order differential equation in terms of psi. Okay. and then I get an equation which is called the Legendre equation. Okay, so this is the d1 minus psi square times d square g by d psi square minus 2 psi dg by d psi plus alpha n into psi is equal to 0. That is the Legendre equation. Okay. And we had assumed a series form for the dependence of g on psi. We had assumed a series form for the dependence of g on psi. From that you will get the dependence of dg by d psi and d square g by d psi square both on psi. Okay. Substitute that into the equation, okay, and this is the equation that I get. The first term is proportional to psi power p minus 2 because there are two derivatives on psi, okay, in the first term here. The first term is 1 times the second derivative. The second term is psi square times the second derivative, okay, and this is proportional to psi power p, okay, as okay, because it is psi power p minus 2 times psi square. The first derivative has psi multiplying it, so therefore it is also proportional to psi power p, and the last term is proportional to psi power p as well. Okay. So I had expanded this equation out, collected terms that are powers of psi power p and psi power p minus 2. So these two terms are proportional to psi power p. The first term is proportional to psi power p minus 2, and in this term the terms for p is equal to 0 and p is equal to 1 are both identically 0. Okay. So I can make the transformation p minus 2 being relabeled as p, which means that p will be relabeled as p plus 2. Okay. For 0 and 1 in p the coefficients are 0. Okay. So therefore when I relabel it p to p plus 2, the summation is from p is equal to 0. Okay. The coefficient is p plus 1 into p plus 2 into a subscript p plus 2 times psi power p. Okay. Now these coefficients are the same on both terms. Okay. The powers of psi are the same on both terms now. Okay. And if I set the coefficient to 0 term by term, I get the coefficient a p plus 2 in terms of a p. Okay. And once I have this, then I can go back and use this series expansion in order to find out what is the solution g. Okay. You can go back, use this series expansion in order to find out what is the solution g. Okay. So basically I have a p plus 2 in terms of a p. That means if I know a0 and a1, I can then find out a2, a3, etc. Okay. I can then find out what is a2, a3, etc. Okay. Now look at this recurrence relation. Okay. Examine this recurrence relation. Okay. In the limit as p goes to infinity, if this coefficient alpha n is finite, okay, in the limit as p goes to infinity, if this coefficient alpha n is finite, then a p plus 2 by a p tends to 1. Okay. A p plus 2 by a p tends to 1 in the limit as p goes to infinity, because p into p plus 1 is p square plus p, and p plus 2 into p plus 1 is also p square time plus, okay, 3p plus 1. Okay. In the limit as p goes to infinity, right, this coefficient goes to 1. Okay. And I have this series. Okay. I have this series which was g is equal to summation of a p psi power p. Okay, I have the series, and the ratio of successive coefficients is 1, okay, in the limit as p goes to infinity. What that implies is that the series does not converge. If the ratio of successive terms is 1, then this implies that, okay, series does not converge for psi is equal to 1, okay, or minus 1. Okay. It means that the series does not converge when psi is equal to 1 or minus 1, because a series in which the ratio of successive terms is 1, okay, a series going from 1 to infinity, where the ratio of successive terms is 1 or even minus 1, is not a convergent series. Okay. So, this does not converge at psi is equal to 1 and minus 1, which corresponds to theta is equal to 0 and pi. Okay. 1 psi is equal to 1, psi is cos theta. So, psi is equal to 1 or psi is equal to minus 1 corresponds to theta is equal to 0 or theta is equal to pi. So, obviously, you do not get finite results for the terms in the series in general in the limit as okay, at psi is equal to plus 1 or minus 1. Of course, if psi is less than 1, of course, then the series converges, because the ratio of successive terms is less than 1. Okay. But at 1 and minus 1, which are the boundaries of the domain for psi, or at theta is equal to 0 and pi, which are the boundaries of the domain for theta, this series does not converge. Okay. There is only one way that this series converges, okay, and that is if this alpha n is chosen such that one of the terms in the series becomes 0. Okay. In other words, if I choose, okay, alpha n is equal to alpha n is equal to n into n plus 1, okay, where n is an integer. Okay. Then I have a p plus 2 is equal to p into p plus 1 minus n into n plus 1 by p plus 2 into p plus 1 into a p. Okay. That is the coefficient, which means that when p is equal to n, right, when p is equal to n, the numerator is equal to 0. Okay. When p is equal to n, the numerator is equal to 0, which means that a n plus 2 is equal to 0. Okay. And because a n plus 4 is related to a n plus 2, I will get a n plus 4 is equal to 0, and then a n plus 6 is equal to 0, and etc. Okay. So, all the coefficients become 0 for n equal for a n plus 2 and higher. Okay. And since all of these coefficients are 0, the series is convergent, because now it is a sum of a finite number of terms, finite number of n terms. All higher terms are 0. Okay. So, therefore, the fact that the series has to converge, has to have a finite result at psi is equal to 0, psi is equal to 1 or psi is equal to minus 1, fixes the form of this coefficient alpha n here. Okay. Fixes the form of this coefficient alpha n as n into n plus 1, where n is an integer. Okay. So, therefore, alpha n has to be equal to n into n plus 1. Okay. So, those are the eigenvalues, okay, of this relation. Okay. So, I told you that in this series expansion, okay, the coefficients a0 and a1 are fixed, and then a2 is determined in terms of a0, a3 in terms of a1, and so on. Okay. So, if n is finite, I can get a finite result if n is even, for example. Okay. If n is even, then I can set a1 equal to 0, in which case all odd coefficients are equal to 0, okay, and the series of even terms, okay, the series of even powers of psi gets truncated at n, and you get a finite result. Okay. and those terms are even powers of psi, therefore, they are even functions of psi. Okay, they are even powers of psi, that means that they contain psi power 0, psi power 2, 4, etc. up to n. That series truncates at n. If it is odd, then you get odd powers of psi 1, 3, etc. And if n is odd, that series truncates at n, and that is how you get a finite result. Okay. This finite result for different powers of n are what are called the Legendre polynomials. Okay. P1 of psi is equal to P1 of cos theta. Sorry, Pn, my apologies. For each value of n, this series truncates at n. Therefore, Pn of psi is an nth order polynomial in psi, okay, because it truncates at n. Okay. If n is odd, then this contains only odd powers of psi. If n is even, it contains only even powers of psi. Okay. So these are the Legendre polynomials for different values of n. Okay. And you can calculate this using this recurrence relation. Okay. You can calculate this using this recurrence relation. Okay. I will not go through the details of the calculation, but P0 of psi is just equal to 1. Okay. P1 of psi is just equal to psi. Okay. P2 of psi is equal to half of 3 psi square minus 1. Okay. Etc. Okay. These are of course known only to within an unknown constant, because we have a linear equation for g. Therefore, if you multiply this by any constant, this will also be a solution, okay, because it is a linear equation. So, I can multiply these polynomials by any constant and you will still get a solution. The constant normalization that has been used here is that P naught of psi is equal to plus is equal to 1 at psi is equal to 1 and is equal to plus or minus 1 at psi is equal to minus 1. Okay. So, the odd functions are odd polynomials are minus 1 at psi is equal to minus 1, and even polynomials are plus 1 at both the psi is equal to 1 and minus 1. Okay. Now, these are orthogonal polynomials. Okay. So, you can show that they are orthogonal polynomials quite easily. I will not go into the details here, but they do satisfy the orthogonality relation. Integral d psi Pn of psi Pm of psi is equal to 2 delta n m by 2n plus 1. An alternate way of expressing this is that integral sin theta, okay, this is from minus 1 to 1, okay, the boundaries, or in theta this will be from theta is equal to 0 to pi. Okay. So, that is the orthogonality relation for the Legendre polynomials. Okay. Yeah. Okay, so these are the solutions, the Legendre polynomial solutions for the theta direction. So let us return to our problem. Okay, so let us return to our problem. If you recall, my problem was 1 by r square d by dr of r square partial t by partial r plus 1 by r square sine theta. This is equal to 0. It substituted t is equal to f of r g of theta. Okay. And then we had got 1 by f multiplied the equation by r square divided by f times g d by dr of r square df by dr plus 1 by the solution in the g direction was that this equation, okay, 1 by g sine theta minus plus alpha n square is equal to 0. Okay, so, yeah, plus alpha n, I am sorry, okay, is equal to 0. And from the condition that the series has to be finite, we found that alpha n has to be equal to n into n plus 1, where n is an integer. Okay. So, that was the condition that we had obtained here. Okay. So, this has to be n into n plus 1. So, now what that implies is that the solution for g is equal to p n of cos theta. Okay. What is the solution for f? Okay. What is the solution for f? Okay. That I get by substituting that into this equation. G is equal to minus n into n plus 1. That means that 1 over f d by dr of r square df by dr, okay, minus n into n plus 1 is equal to 0. Okay. I can multiply throughout by f, okay, and I will get minus n into n plus 1 f is equal to 0. Expand out, you will get r square d square f by dr square plus 2r df by dr minus n into n plus 1 f equals 0. Okay. So, if I just expand that out, this is what I will get. Okay. This equation, as you can see, has 0 net dimension in r. Okay. I have r square d square by dr square and r times d by dr. Okay. So, therefore, I can try a solution of the form f is equal to r power a. Okay. If I try an equation of the form f is equal to r power a, right, then I will get a into a minus 1 r power a, r square. If I take the second derivative, I will get a into a minus 1 r power a minus 2 and then multiply by r square, okay, plus 2a r power a minus n into and you can combine these two terms. A square minus a plus 2a is a square plus a, which is a into a plus 1 r power a minus n. And there are two solutions of this, one of which is obvious, a is equal to n. The other is that a is equal to minus of n plus 1. Okay. This is not as obvious, but quite easy to work out. Okay. You just substitute a is equal to minus n plus 1, a plus 1 will be equal to minus n, and you will get an n into n plus 1 on the first term. Okay. So, these are the two solutions, which means that f is equal to some coefficient times r power n, okay, plus some other coefficient by r power n plus 1. Okay. For integer values of n, okay, for integer values of n. Okay. Therefore, my solution for the temperature has to be equal to f times g, a r power n plus b by r power n plus 1 p n of cos theta. Okay. This satisfies the equation for any value of n, okay, because the radial part becomes minus n into n plus 1, the theta part becomes n into n plus 1, the two sum to 0. Satisfies for any value of n. It satisfies the condition that the temperature has to be finite at theta is equal to plus 0 or plus pi for any value of n. Okay. Therefore, the most general solution is the summation of these from n is equal to 0 to infinity of a n and b n. Okay. Okay, so, that is the most general solution for the temperature field. Okay. How do I find out the coefficients? Okay, those have to be determined from the boundary conditions. Okay. What are the boundary conditions? Okay. At r is equal to capital R, the temperature Tp is equal to Tm. Okay. Recall that we had solved this Laplace equation for both the particles and the matrix. Okay. The equation for the temperature was exactly the same in both the particles and the matrix. Okay. Okay. Yeah. Yeah, here. Since there are no sources or sink in either the particles or the matrix, the temperature in the particles is Kp del square Tp equal to 0. Temperature in the matrix is Km Laplacian of Tm is equal to 0, and therefore, Laplacian of Tp is also 0, Laplacian of Tm is also 0. So, the temperature field satisfies the Laplace equation in both the particles and the matrix. Okay. Therefore, the solutions that we had obtained apply for both the particles and the matrix. Okay. So, if I write the temperature separately for the particle and the matrix, I will get Tp is equal to sigma a n p r power n plus v n p by r power n plus 1 p n of cos theta. Okay. And Tm is equal to sigma of a n m r power n plus where the superscripts p and m in the coefficients a n and b n represent particle and matrix respectively. Okay. So, these are the solutions in the particle and the matrix. Okay. At r is equal to r, we have the temperatures are equal and the k particle times partial T particle by partial r is equal to k matrix. Okay, so, those are the two conditions at the interface, and as r goes to infinity, T is equal to T prime into Z, which is equal to T prime into cos theta. So, that is the temperature in the particle and the matrix. Okay. So, using these boundary conditions, we have to determine what is the temperature field in the particle and the matrix, and from that what is the correction to the flux in the particle and the matrix. So, I will continue this in the next lecture. Okay. I will see you then.